Hello everyone, welcome to the next lecture on theory of computation, and in this lecture we will be seeing the formal definition of NFA or non-deterministic finite automata, and we will also try to understand what it means with the help of an example. Alright, so let's get started. Okay, so here we have the example of NFA, and what is this NFA? It is actually a machine which accepts the set of all strings that end with 0. And how do we know that? If we look at this, we see that on getting 0, it comes to B, which is the final state represented by double circles. So we know that it is a set of all strings that end with 0 that is accepted by this NFA. Alright, now let us just observe this NFA and try to figure out what is the difference from the DFA. So if you look carefully, you can see that there is a starting state represented by this arrow. So A is the starting state, just same like the DFA. And A on getting input 0, what happens? It could either stay in A itself or it could go to B. There are multiple next states. This was not possible in DFA. And A on getting input 1, it stays in A itself. And what about B? We did not mention what happens to B when it gets input 0 or 1. Is it wrong or is it incomplete? No, it is not wrong. In NFA, you can actually leave it like this. It is perfectly legal to leave a state like this without mentioning anything. That actually means that this state does not go anywhere. Alright? Which was not legal in DFA, but in case of NFA, it is perfectly legal, and this is a complete NFA. Alright? And by looking at this, you can guess that it is very easy to design a NFA as compared to DFA, because in DFA we have to be very careful about sending the states to only one next state, and we should also mention clearly on getting input, whatever inputs they are, we should show what is the transition from each input. But in NFA we find that even if you leave it like this, it is complete. So it is very easy and straightforward to design a NFA. Alright, now let us try to give the formal definition. So just like DFA, NFA also is defined using 5 tuples, which are Q, sigma, Q naught, F, and del. Using these 5 tuples, we can define our NFA. And what are these? Let me write it down. Just it is almost the same like DFA. Q is the set of all states, and sigma is the inputs, and Q naught is the start state or the initial state, and then F is the set of final states, and del. So we saw that this Q, sigma, Q naught, and F, it is same like the DFA that we have already studied. And what about del? Del is a transition function that maps Q cross sigma to what? We'll try to find out what this is. I'll leave it blank here. We'll try to find out what does this transition function del map. Alright, that is what we are going to find out. Okay, so Q, sigma, Q naught, and F are the same like DFA, so I hope I don't need to explain it again. So let us just try to write down the values for this particular example. So in this particular example, what is Q? Q is a set of all states. So what are the set of all states here? The only states we have are state A and state B. So it is A and B. Alright, and sigma is the inputs. So what are the inputs we have? The inputs we have are zeros and ones. The inputs are 0 and 1. And Q naught is the start state or the initial state. And how do we know which is the start state? The state that is pointed by this arrow coming from nowhere shows that this is the start state. So the start state is A, which is also known as the initial state. And what is F? F is the set of final states. So here we have only one final state, that is B, represented by the double circle. Now, what is del? How do we find out what is del? This is what we are going to find out. Okay, so when we try to find this out, let us try to do some exercise. Let us see. Let us check for state A. State A, on getting input 0, where does it go? It goes to state A itself, and state A on getting input 0, it also goes to state B. Alright? And let us see, when state A gets input 1, what happens? When state A gets input 1, it goes to state A itself, right? And yeah, that's it for state A. And what about state B? State B on getting input 0, where does it go? It does not go anywhere, so we represent it with phi. Alright? And what about state B on getting input 1, where does it go? It again goes nowhere, so it is again represented by phi. So we see that given a state, when it gets a particular input, it can either go to one state or more than one states. So we see that A on getting input 0, it went to two states, A and B. And A on getting input 1, it went to just one state. So there are many possibilities. Let us try to figure out how many possibilities are there. Suppose for this example, A and B are there, and let's see what are the possibilities that we can get. So let's talk for one state A. A on getting a certain input, let's say 0 or 1, whatever it may be, on getting a certain input, it can either go to A, right? Or it can go to B, right? Or it can go to both A and B, like here it went to both A and B, right? So it can either go to A, it can either go to B, or it can go to both A and B, or it can also go nowhere, just like we saw that B was going nowhere. So this A on getting a certain input, it has these four possibilities. It could either go to A, B, AB, or phi, right? So there are four possibilities. Now let's take another example. Let's say that we have three states. Suppose we have three states. All right, we have three states which are A, B, and C. Now in this example, suppose in state A we get a particular input. So what are the possibilities to which A can go? A can either go to A itself, it can go to B, or it can go to C, or it can go to A and B, right? Or it can go to A and C, or it could go to B and C, or it could go to all of them, A, B, and C, or it could not go anywhere, it could go to phi. Okay, so we see that when there were three states, we had 8 possibilities. When we had three states, there were 8 possibilities. 1, 2, 3, 4, 5, 6, 7, 8. And what about this case? This was for this example. And in this example, how many states we had? We had 2 states. We had 2 states, and how many possibilities we had? 1, 2, 3, 4. 4 possibilities. So seeing this pattern, can we figure out a formula for this? We see that when there are 2 states, it has 4 possibilities, and when there are 3 states, there are 8 possibilities. So we can say that it is 2 raised to power 2, this is 4, 2 raised to power 3, this is 8. So we can say that this transition function, it maps q cross sigma to, can you guess it? Yes, I hope you have guessed it. It is 2 power q. 2 power q. That is 2 power the number of states. So that is what our transition function maps to. In case of DFA, it was q cross sigma to q, because every state, it leads to only one next state. But in this, every state can lead to multiple next states, and it has 2 power q possibilities to choose from where it can go on getting a particular input. Alright, so that was the formal definitions that we could give to our NFA. It is defined using 5 tuples: q, sigma, q naught, F and del, where Q sigma, Q naught, and F the same as DFA, and the only different thing is the transition function del, which maps Q cross sigma to 2 power Q. So I hope this made the formal definition of NFA clear to us. So in the next lecture, we will be explaining about this particular example in a more detailed way, which will make it more clear to us. So thank you for watching and see you in the next one.